This is MEI Statistics Minor chi-squared tests, and our final video 1.4 chi-squared test for goodness of fit. So our process for testing goodness of fit is as follows. First, we determine which distribution would be most appropriate. For instance, uniform, binomial, Poisson, geometric. This is very important. It's often overlooked and seldom tested. If you don't have a good contextual reason for this model, you shouldn't be testing it. We then form our hypotheses. We declare the significance level before we do the test. We estimate any required parameters from observed data. So if any parameters are missing, you will need to estimate them. We then calculate the expected frequencies. We combine expected frequencies so that none are less than 5, just like with the contingency tables. All chi-squared tests have this requirement. We then calculate the test statistic, and again it's exactly the same as for the contingency tables. We find the number of degrees of freedom. We find the critical values from the tables or on a calculator. Then we see if the value is significant and draw conclusions in context. So example 1, it is thought that this model, the binomial distribution, with 10 trials and 0.2 probability of success, would be a good model for the data in the following table. Conduct a test to see if this is a good model. Use a 10% significance level. So the first step, decide which model is suitable. Well, there's no need to do that. Someone's already done it. They're telling you the model that they think is suitable. So hypotheses first. H0 is that this binomial distribution is a suitable model for the data. H1 is that this distribution is not a suitable model for the data. Declare the significance level. It's already been done for us. And note that n is equal to 100. We can do that by adding up the frequencies quickly. So we need to work out the expected values using probabilities from this binomial distribution. We can get them from tables, or our calculator, or GeoGebra. Note that 9 and 10 to this level of accuracy is 0, so we don't need to worry about them. So back to our table, I'm going to rename the frequency to observed. This is our observed frequency. We now add in the probabilities that we found from our calculator or GeoGebra. And now we need an expected row. So for x equals 0, if the probability that x equals 0 is 0.1074, then we would expect there to be 0.1074 times 100, which is 10.74. So our model would predict that there should be a frequency of 10.74 for x equals 0. So we simply multiply the probabilities by n to get our expected values. So we need to check that e is greater than 5. As we can see, there's several values here that don't fit. Will 5 plus work? Well, if we add all these up together, we're still only going to get 3.28. So a 5 plus category still won't work. So we're going to need a 4 plus category to make sure all of the expected values are above 5. So we add up the observed and the expected values and put them in a new table. We now need to calculate the contribution to the test statistic. So the contribution is observed minus the expected squared divided by the expected. So for x equals 0, that is 12 minus 10.74 squared over 10.74, which is 0.1478 to 4 decimal places. Remember to go accurate to decimal places so the same level of accuracy is throughout. So there are all the contributions to the test statistic. So our test statistic is the sum of all these values on the calculator, 1.5453. Now before we can find the critical value, we need to calculate the degrees of freedom. The degrees of freedom here is defined as the number of categories minus the number of constraints. So here, as you see, we have 5 categories. We only have one constraint, and that is the number of data points. So these first 4 values have the freedom to vary, but this one does not, because it needs to make the total correct. So that is our only constraint. So that is 1. So the number of degrees of freedom is 4. We use exactly the same table in the formula book. Again, the left-hand side is a red herring. We have a 10% significance level. Our degrees of freedom is 4. So we go along from 4, down from 10. Our critical value is 7.779. Again, many graphical calculators can also do this. Our critical value is 7.779. Our test statistic is 1.5453. You can see that's well in the insignificant range. So it is not significant, and we can accept H0. So our conclusion, there is insufficient evidence to suggest that the binomial distribution with 10 trials, 0.2 probability of success is not a good fit. Note that there is not evidence that this is a good fit. This is the reason why we only try to fit models with a good contextual basis, because we are not proving that it is a good fit. So, example 2, I recorded the number of text messages that I received each day for 120 days. Is a Poisson distribution a suitable model? Test at the 5% significance level. Note here that lambda is not given. We're going to have to estimate that from the data. This can happen for any distribution. Here we're using Poisson, but equally it could be an unknown binomial or geometric probability, for example. So, which is the most suitable distribution? We don't need to worry about that. Again, they've given us the distribution. So our hypotheses, H0, the Poisson distribution, is a suitable model. H1, the Poisson distribution, is not a suitable model. So to find lambda, we're going to have to find the mean of the data. So I'll multiply x by the frequency. So 0 times 2 is 0, 1 times 32 is 32, and so on. So the total equals 282, and so therefore the mean, which we remember is our value of lambda, our predicted value of lambda, is going to be 282 over 120 days, which is 2.35. So again, I'm going to change my frequency row, in this case the number of days, into an observed value. My probabilities are going to come from the calculator or the formula book or GeoGebra. There's a small issue here though. If you add up those probabilities, they add up to 0.995. And you think, well, that's quite close to 1, but it's not quite there, is it? Is there a rounding error? Possibly. But if you use more accurate figures, you're going to get 0.997055. So a bit closer, but still not there. The error comes here from the fact that the possible values of Poisson distribution go up to infinity. So we're going to need another column, an 8+ column. So anytime you're using the Poisson, you need to remember that those higher values need to be considered as well, even though there aren't any observed. So we calculate the expected values by multiplying the probability by 120. We have some expected values below 5. Combining 6, 7 and 8 isn't going to get us far enough, so we're going to have a 5+ category. Our contribution to the test statistic, again, so for x equals 0, we're going to have 2 minus 11.44 squared over 11.44, which is 7.794 to 3 decimal places. Our test statistic is the sum of all those values, which is 11.965. For the degrees of freedom, we can see we have 6 categories. We know that it was over 120 days, so that is a constraint. We have also calculated lambda to be 2.35. That means that this data not only has to have expected values adding up to 120, they have to have expected values with a mean of 2.35. So that is a second constraint. So our degrees of freedom nu is equal to 6 minus 2 constraints, which is 4. At the 5% significance level, with 4 degrees of freedom, we get a critical value of 9.488. So 9.488 is there. 11.965, our test statistic, is there, and that is in the critical region. So that is significant. So we reject H0. So my conclusion, there is significant evidence to suggest that the Poisson distribution will be an unsuitable model for the number of texts received in a day. We still need to mention evidence. It should never be definite in conclusion. So that's the final video on chi-squared tests.